I designed this crank to be a crossplane crank because I love the sound of the crossplane. Now most inline 4-cylinder 4-strokes, they have a flat plane, meaning all the throws are in a flat plane. And they do that because it gives you an even firing order. Now, if you go moving your throws around, your firing order gets lopsided. Now, the crossplane does have a lopsided firing order, and that's what gives it its distinctive sound. Still haven't decided on the lubrication for this thing yet. I'm seriously considering boring some holes and have forced lubrication. And I think that would be really cool if I could do that, but it's going to be a lot of work, and hopefully I don't break a damn drill bit off in the crank that I spent so long making. The other option would be to, I don't know, maybe put grease zerks on the bearing caps and pump grease into it every now and then. I'm not sure I like that idea. So I have this red brass. This is going to be the bearing. And to hold the bearing, I need some pillow blocks. So I'm machining some pillow blocks out of some aluminum that I poured. There's the rough edge you can still see. And I got them somewhat flat. I will have to put these in the 4-jaw chuck and true the surfaces. But right now I'm just doing a basic layout and seeing what it looks like. And here's my layout. So first thing I'll have to do is slit this down the middle, and that's going to make this a football shape. So then I'll have to turn the outside round again and then get it to fit in here. I've got these cool flywheels, big piece of cast iron there, and another big piece of cast iron. Now these are too big and heavy. I'll have to remove a bunch of material off that and lighten it up a bit. And I think this one I'm going to mount a timing gear to it, and that'll be the driver for the cam. This one is going to be convenient to put a governor on it. I'd like to have a governor on this engine, and this engine is going to turn a generator. If you don't know it, the most important tool in your shop is a toaster oven. All right, YouTubers, I got these squared up pretty good. They're not very cleaned up, but they are square. So I poured these. Now, I don't like to use beer cans and cheap aluminum. I am blessed to live very close to a metal recycle place. I can get all kinds of industrial grade aluminum all day long. And what's really weird is this industrial grade stuff, it machines excellent. It's really next to impossible to put a bad finish on the industrial grade stuff. It cuts so amazing. But once you melt it and you pour it into a mold, something changes. And I believe it's because the industrial grade stuff has been cold rolled through dyes and such, and it changes the crystal structure. And so I think once I melt it and I, obviously pour it into some sand, the crystal structure has changed and it cuts different. And it's really hard to get a good finish on it. But I did get pretty decent finish. I don't know if you can see it on camera, but there's a lot of little pores, little tiny holes in it. And I believe that's because my sand was too moist and there was a lot of air bubbles. I believe anyways. It's just a theory of mine. And if you guys don't know about this awesome tool, this thing is really awesome. This is an optical punch. And some of you guys might not know about this tool. So what happens is when you make your scribe mark and you make a little cross, you can look in here. I doubt this camera is ever going to show that, but well, you can barely see it. There's a glare. There's a crosshair in there, just like the sight on a scope on a rifle. And you look in there and you can line up the crosshairs perfectly. And then you take your optical thing out and you move this over into that hole and smack it, and it's a perfect center punch every time. It's a really great tool. So anyways, that's how we did this. Don't know if you can see that, but those center punches are right on the mark. So next step is to do the tap drill for these. And once I get those holes drilled, I might even tap it. It's not necessary just yet. What I want is the tap holes where they're going to be, and then I'll split this where the bearing splits, and the cap obviously will get, the holes will get drilled bigger so that the bolts go through. There's going to be a countersink because it's going to be a cap screw, so that cap screw is going to countersink in like so. There's the other one. That's the idea. But the trick is to drill these tap holes first, and that way they're true with each other. And then you do the split. Order of operations is very important when you're doing stuff like this. It's easy. If I would have split this first, it would be next to impossible to get those holes drilled perfectly, and yeah, without a bunch of clamps and yada yada. So anyways, that's where we're at. I'm going to get the drilling. All right, here is my mill. This is the MacGyver 2000. There it is right there. Little picture of Johnny Cash behind it. I built this mill a few years ago. It was originally my lathe. So originally the spindle was laying down horizontally. It was actually my third lathe because the first two I built, they worked like dog crap. So this was the third one I built, and it worked really well. But then my South Bend lathe fell into my lap, and I was able to go pick it up for a few $100 and restore it and get it working. So what I did is I chopped the horizontal part off and I lifted the spindle up vertical. It works really well. Now I wouldn't make parts for NASA with it. So this is a 3-jaw chuck, and I got this online for, I don't know what it was, 200 bucks or something, 180 bucks. But everything, oh, and this clamp I got at Harbor Freight. Everything else you see came from Metal Recycle, including the end mill. So I got this big old Acme thread. It's like 2 3/8. It's a huge hogging thing. That controls my elevation of my spindle. I can't elevate the table. I just have X and Y axis. The table I got at the Metal Recycle. It was laying there, and I think I paid like 40 bucks for it. I can't remember. They weighed it at 145 pounds. That was a cool score, and that's what really inspired me to do the mill thing. And of course, once I got the Acme thread, that gave me a way to elevate it, because I didn't know how to elevate all this. So basically, I just used 1/2 inch all thread. This controls that axis. Over here, I have a wheel. Controls that axis. And these hand wheels, that came from the Metal Recycle. It was on a like a water valve. Let's see, this part I poured. This shaft was, I think it's a 1 5/8 or something. I can't remember what the size was. I couldn't find the right size bearing, so I poured my own bearing. I had a grease zerd in there, but stupid Harbor Freight grease gun broke my grease zerd off because it got stuck on there and wouldn't come off. I got this at Tractor Supply. Coincidentally, this was like 1 3/8, and so they had like one of these on the shelf, and I bought this bearing from Tractor Supply. And so this is kind of a keeper thing that keeps the shaft elevated where it's supposed to be. We come down. I don't have a thrust bearing here. I wish I did, but anywho, this works good. And I don't know if you can see that on the camera, but there's a tram setting to adjust my tram. This belt pulley was the original pulley driver. I'm sorry, not the driver pulley, but it was the one that drove the spindle in my lathe. But when I did the vertical thing and I made some gears, I'm going to show you that in a second. I left this on because it makes a good flywheel to keep the spindle, you know, rotating smooth. I don't want like little jerkiness in it. So this is good for keeping that spindle nice and smooth when it turns. Looking above, there's the motor, and it's got a V-belt that goes back to a shaft, the primary shaft, and it goes down to a rack of gears. You can't really see it, but there's the primary shaft coming down with the rack of gears, and I poured and cut all of these gears. Looking from the face again. So this is a counter shaft, and it has a rack of gears, and there's the output shaft right here. So this gear, I can elevate it and put it into one of 3 positions, and it gives me 3 speeds. And then down underneath on the bottom of the output shaft, I have a belt pulley. It's a flat belt pulley, and I don't know if the camera will show that, but that's a serpentine belt, and I've got it turned inside out so the grooves are on outside. there's a, what you want to call it, an idler pulley. And that keeps the tension on the belt. And it comes out here to the spindle and runs a spindle. And I have two ranges, so kind of like a drill press. I can move the belt up and get a much faster speed out of it. I'm getting ready to put this slitting saw in here. This will go up in the chuck. I'll de-elevate this thing down here somewhere. And we're going to slit that bearing with this. I highly do not recommend this vise. I got plans to make a proper machinist vise. Just haven't got there yet. Alright folks, I've gone as far as I can go on the slitting saw. I'll have to take it over to the bandsaw and get a nice straight cut in the kerf and cut these off. I only need 2 inches off this, and seeing as brass is pretty valuable, I'd like to save this butt end that's pretty solid. I'll make a bearing out of that for another project. Alright folks, here's the final product of the pillow block and bearings. I got this machined really nice. I'm kind of proud of myself. It's a really good fit. On this end, this is what it looks like. It's turning really nice. I'm not really good at making stuff pretty. I never had the patience to really take the time to keep things pretty. These pillow blocks actually looked really nice when I machined them, but after drilling a bunch of holes in it and boring it and doing a bunch of work to it, it just keeps getting dinged up. It gets dropped, or something gets dropped on it. Yada yada. So anyways, now in the past I have made crankshafts the wrong way, and usually when I screw up a crankshaft, you can see it really easy when I put the bearing on and spin it, and you'll see the pillow block move around, and that's how I know shit ain't right. But anyways, I got these really straight. They don't move at all. The thrust is like dang near perfect. It's so snug. I got it full of gear oil in here, and the gear oil doesn't leak out. Like, that's how good the fit is. Really happy with that. So I pulled the cap screws, and I'm going to show you folks what's going on. This crank is going to get forced lubrication. So I've got a copper tube, a stub sticking out that I can attach the oil plumbing to later. And when we take it off, there's what's up. You can see the hole in the center with the oil channel. And that oil channel goes all the way around right there. So this so-called red brass was not easy to machine. It wore out my high-speed steel tools pretty quick. Kind of like stainless steel. It was a lot like cutting stainless steel. When you do cut it, it cuts really nice. But if your tool isn't sharp, man, it gives you all kinds of problems. I eventually had to use my carbide because the high-speed steel just wasn't quite up to par to give me the finish that I wanted. Carbide did definitely give me a nice finish. Eventually, I'm going to drill holes through this crank, and so it'll be fed from this. There'll be a hole in the crank that will deliver it to the crank rods. And I think I'm going to try drilling a hole up through the crank rod so that the oil can get to the wrist pin. Alright folks, here's what's up. I'm sketching this motor together. Here's the crank. I have here a piece of 4x6 square tubing steel, and I think I'm going to try to use this for a crankcase. I painted it so it wouldn't rust while I'm working on it. It's also nice for making my scribe marks. So the idea is, nice sound. That's going to go in there like so. So my pillow block is a little tall right now. I'm going to cut this down, and this crank will come down a little bit more. And it's going to make the crank rods a lot longer. I think they're going to be about 4 inches. These cylinder sleeves are so small in diameter, I need a longer crank rod in order for it to reach up without hitting the sides of the cylinder. So as your rod gets shorter, the angle gets sharper and it's going to hit the side of the cylinder. At least I did all that on paper with pencils and compasses, and I was able to figure out how long the rod needs to be to not hit the side of the cylinder, and 4 inches seems about right. So I also need room for my cam gear. The cam gear is going to be pretty big. It's going to be on the outside of this, and the profile is going to be more like this on the end. And I'm really considering having this be open on the end and actually cut this back like so, so that the pillow block is exposed, but leave this be a tray so that oil doesn't dribble out and it'll go into the oil pan. I started with a Panther Pup Blueprints, and it's an air-cooled engine, but I really want this to be water-cooled. But originally I did think this might work, and then make an air shroud and have a fan blow air on this, but I really want to go water-cooled. So these are the water jackets, and I have stainless steel cylinder sleeves. I'd like to offset these cylinders because I'm going to have lifters right here, push rods, rockers, all kinds of moving stuff. Now this will get cut back to a proper length. I'm just not 100% sure of the length yet, so obviously I cut it long for now until I'm 100% sure where I'm going to cut it. I'm going to cut some inspection plates, probably 2 of them, and of course the frame will be, it'll stay connected down the middle, but it'd be nice to inspect the crank rods. It's also going to have an oil pan cut in the bottom of it because I got to have a way to fasten the crank rods. So I got to be able to come up through the bottom and be able to turn the cap screws on the crank rods. What's nice about this steel is I can weld on it. So that is why I'm kind of preferring the steel over pouring an aluminum crankcase. If I pour an aluminum crankcase, I know I'm not going to get it right the first time. Probably going to have to pour 2 or 3 of them. And then there's all the things like the bosses to drill and tap and have mounting points with bolts and such. There'll be all kinds of that stuff to mess with. With steel, I don't have to worry about it. It gives me a full canvas to weld anything that I need anywhere I want. And I can make bosses real easy. I can just weld a nut to this, or I can drill and tap this, and that will be the boss. That's going to be the case for the cylinders. They will get held down with a tapped hole in this. If you enjoy this, keep on watching, and in the next few months or so I will keep videoing my progress on this engine, keep you updated. Thanks for watching.